Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the geometric distribution. So this is another type of discrete probability distribution. We saw the uniform distribution and did a lot of work on the binomial distribution. So like the binomial distribution, the geometric distribution is discrete and involves multiple independent Bernoulli trials. So when things are done with replacement. But unlike the binomial distribution, which calculates the probability of a certain number of successes, that's what the binomial distribution does, the geometric distribution calculates the probability that the first success will occur on the xth trial. So this is the kind of question for which we'd use the geometric distribution. So picking cards randomly with replacement from a normal deck of 52, no jokers. What's the probability the first heart will be picked on the fourth draw? So here, we're not calculating the probability we will get a certain number of hearts as we did with the binomial distribution. We're figuring out the probability that the first heart will be drawn on a given trial. So here, the random variable is the number of trials. So this is the formula we're going to use to calculate the probability, and we've also got expected value and variance formula. But let's just look at this intuitively. So the probability the first heart is on the fourth draw. Well, that means that the first draw is not a heart. The probability you don't get a heart is 3/4. Then the second draw is not a heart. Then the third draw is not a heart. And then the fourth draw is a heart. The first draw of a heart is on the fourth trial. So making this easier, we could write this as 3/4 to the power of 3 times by 1/4. So the probability of success needs to be the same on each trial, just as it did for the binomial distribution. Each trial, probability of heart is 1/4, not heart is 3/4. So here you can see there would have been an easier way to do this. It's just the probability of failure, and the power is the number of trials minus 1. So here we wanted 3 trials where we don't get a heart and 1 trial when we do get a heart. And that's how this formula comes about here. So here P, the probability of success, is again 1/4. So 1 minus P is 3/4. So it was 1 minus P to the power of x minus 1. Here little x is 4. Because that's the number of trial that we're interested in. We're interested in fourth draw or the fourth trial. So 1 minus P to the power of x minus 1 multiplied by P. You have this many trials where you fail, and then you get a success on the next trial. So that's how you calculate probabilities like that. So this one would just give me 27/256. That is the probability. So what would EX be? Well, remember, big X, the random variable, is the number of trials. So the expected number of trials is 1/P, 1/1/4, which gives us 4. So this is saying if I keep picking a card randomly from a normal deck with replacement, I would expect that it would take me 4 trials before the first success. And that makes sense. That's saying that every fourth draw that I would expect to get a heart. Every fourth draw. So the variance of x, well, we're just going to use that formula here, and don't worry about how it comes about. We're not going to go into that. It would just be 1 minus P over P squared. So the answer you get there is 12. Of course, that means the standard deviation of x will be the square root of 12, which is about 3.46. So that's sort of the average distance from the mean. Like on average, it will take between 0.5 and 7.5 trials to get a heart. That's a crude interpretation of the standard deviation, but that's basically what it's saying. All right, let's look at one more example where we're using this formula. So let's try this question here. I roll a die until the first number greater than 4 comes up. What's the probability that this happens on the 7th trial? We'll also find the expected number of rolls. So if we let x, the random variable here, be the number of trials required for the first 4 to come up. So here x follows a geometric distribution. So it follows a geometric distribution because this is multiple Bernoulli trials. They're Bernoulli trials because each time you roll the die, you can either get a number greater than 4, success, or not get a number greater than 4, which is failure. So 2 possibilities. So it's multiple Bernoulli trials, and we're after the number of trials before the first success. That's what the geometric distribution is all about. So the parameter we need to know here is the probability of success each time, and that's a third. Each time you roll the die, the probability of getting a number greater than 4 is 1/3. So what's the probability that this happens on the 7th trial? So this is the formula for the geometric distribution on the previous slide. So here we have that little x is equal to 7. X is equal to 7 because we're after probability something happens on the 7th trial. So P is a third, probability of success is a third, so the probability of failure each time is 2/3. So the required probability is probability of failure to the number of trials minus 1. We want 6 rolls in a row that are not greater than 4, and then we want 1 roll that is greater than 4. And putting that on our calculator, we get about 0.029. So what is the expected number of rolls required? The expected number of trials? Well, that is just 1 divided by the probability. 1 divided by a third, which is 3. That makes sense, because if the probability of getting a number greater than 4 is a third, we expect that 1 in every 3 trials will come up with a number greater than 4. So we expect we'll have to roll the die 3 times before the first number greater than 4 comes up. We expect that the number greater than 4 will come up every 3rd roll. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.